You'll see these images and these videos often circulating online where there's this kind of cloud-like cone structure around an aircraft, and it is very often captioned as, here's this fighter jet breaking the sound barrier, for example. And I've got a lot of problems with those types of comments.
This podcast is sponsored by Siemens Digital Industry Software. Learn more about their simulation and test solutions by clicking the links in the description. Build a better tomorrow faster with SimCenter. Welcome to a new episode of the Engineering Mind podcast. I'm your host Jousef, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I am very delighted to welcome Dr. Chris Combs to my show. Dr. Combs is the D. Howard Endowed Assistant Professor in Aerodynamics in the UTSA Department of Mechanical Engineering. Prior to starting at UTSA, Dr. Combs worked as a research assistant professor at the University of Tennessee Space Institute. His primary area of research interest is in the development and application of non-intrusive diagnostic techniques for compressible flows, and he also has extensive experience in investigations of hypersonic boundary layer and SWBLI flow physics. On this podcast, Chris and I talk about aerothermodynamics and the different types of Mach regimes, how a Mach 7 test facility works. We also cover measurement techniques such as the Schlieren Method. We talk about the common misconceptions about shockwaves and what the so-called expansion fans are, and so much more. If you would like to support the podcast, make sure you give this episode a like and leave a comment down below to make sure the ominous algorithm is suggesting the video to more inquisitive scientists all around the world. Subscribe if you haven't already. And now, ladies and gentlemen, enjoy my podcast with Dr. Chris Combs. Hey Chris, welcome to my show.
Hi, thanks for having me.
Yeah, it's really a pleasure to have you on the show. So today we will talk about fascinating topics like hypersonic flight, also commercial flights, thermal effects when it comes to hypersonic flights, and a lot of boundary layer theory, things like that. But before we jump into the really interesting stuff, can you talk about who is Chris and what do you actually do?
Yeah, so I am an assistant professor at the University of Texas at San Antonio. My background is in aerodynamics, high-speed flight, a little bit of combustion, and a lot of development of non-intrusive measurement techniques, which I think we're going to get to. I'm an experimentalist at heart. I built a Mach 7 wind tunnel here at UTSA, which is a pretty unique facility and a neat capability. And so I run a lab here where we do hypersonics research and train graduate students that are going after PhDs.
Very interesting. So you already talked about that you're experimentalist. So you have, I think, it cost like $1.5 million, like a Mach 7 test facility, which is super impressive. I saw some images on the internet. Could you explain like what it actually does, what it is used for, and how does it even go up to a Mach 7? How does it
work? Sure thing. So one thing that I kind of like to tell people is that facilities like a hypersonic wind tunnel often are mechanically less complex even than like a low speed tunnel, because they would have a large fan and a motor, and there's a lot of effort that has to go into sort of cleaning up the flow, getting the turbulence levels very low. In a facility like ours, mechanically it is quite simple. You have basically high pressure on one side, low pressure on the other side. And our wind tunnel is called a Ludwig tube design. And so you have a high pressure and low pressure side separated by a diaphragm, just a thin sheet of metal that we score with basically a cross pattern in it so that it will burst at a predetermined pressure, plus or minus some uncertainty. And so we install that diaphragm, charge up the high pressure side, pull a vacuum on the low pressure end, and then that diaphragm will burst when we get up to our operating condition. And just downstream of the diaphragm is our nozzle. It's a converging, diverging nozzle, just like you would see on, say, a rocket nozzle or something like that. And what that does is it compresses the flow to high pressure, and then allows that to accelerate to Mach 1 at the throat. And the throat is that narrowest constriction in the nozzle, which for our facility, because the area ratio to get a Mach 7 flow in a wind tunnel is almost 200 to 1, that is about a 1/16 of an inch thick at our throat. So very, very small constriction that the air goes through. And then once you have that air choked at Mach 1, you can then expand the geometry and that nozzle fans out, like you see in a rocket nozzle. And that allows the air to accelerate up to actually about Mach 7.2 is where design works out. And then we have just a square cross-section test section where we make our measurements. We install models there. And we use that flow to experiment with new measurement techniques or study aerodynamics of a given configuration. But yeah, it's a neat facility. It's pretty unique. We can run to kind of a wider altitude range than a lot of similar facilities. Probably about 20 to 50 kilometers is sort of our wheelhouse for what we're designed to operate at. And it's a student-driven facility. The students are able to go down there and run. We're almost up to 200 test runs now, and we've only been operating since about April. So we are in there testing every day. Duty cycle is only about an hour between tests, and it's really just how long it takes to take apart basically take out the diaphragm and replace it. And that really is our only expendable in our test, or those little sheets of metal. It's less than $20. So we can run pretty cheap, pretty regularly. The downsides of facilities like this are that one, the test times are very short. So everything we do, there's a focus on very high speed acquisition. So people see videos and things that I post, it's usually at 100 kilohertz or higher, because we get 50 to 100 milliseconds of steady test time per test, which sounds very short, but that's a long time in a hypersonic flow. That's about 2,000 flow lengths for a typical model. So it's more than enough time to make steady state assumptions, but it is fast. And so we have to measure things very quickly. And also it's cold. We heat up our flow to about 700 K before test. But even when you do that, the free stream is still cryogenic when it's expanded through the nozzle, because all of that energy is sapped up in that, basically in the kinetic energy, and you lose a lot of that heat. But then the wild thing is, even as cold as the free stream flow is, if you put something in the tunnel, it will tend to heat up. All right, so there's like a positive heat transfer into the model because of the shock heating and the air heating that's happening. So it's a really interesting facility to work in. It gives us an academic capability to do a lot of research that not a lot of people have. And it's really been a workhorse so far. So we've been excited to see how things have been going.
Sounds very exciting. When it comes to the laser-based measurement techniques, could you maybe go into a little bit into detail how that actually works?
Yeah, for sure. So when you're studying hypersonic flow, or really any fluid flow for that matter, there's a long history of intrusive probe-based measurement techniques that you can use, where you have some physical probe that you place in the flow and that measures something like pressure, temperature, velocity, for example, maybe something like a pitot probe. And those are great. They give you a pretty robust capability, but there's a couple downsides. One, there's the fact that, all right, now you're placing something in the flow, you're changing what you're measuring, all right? So you are interfering with the flow itself to make your measurement. That's not ideal. Doesn't mean that those measurements are invalid, but it's not perfect, and it kind of limits what you can do. Also, unless you have a rake of these probe type measurements, some maybe 2D or 3D rake with a bunch of these sensors stacked on top of each other, which again, that becomes more intrusive, then you've got limited resolution in your measurement. Maybe this is the 1D point measurement, maybe it's a 2D line. Very tough to get a real meaningful 3D measurement. But even then, you're still looking at probably a grid, okay? So what we try and do is develop non-intrusive measurement techniques, all right, where there is no requirement to physically put something into your flow and potentially alter what you're looking at. And you can do this with optics and light and lasers. There's some really clever applications that people have developed where you can use non-intrusive means to measure a wide variety of quantities in a fluid flow. So, for example, if you wanted to measure, say, concentration of some species of interest in a flow, you can actually excite that species with laser light if it's tuned to the right wavelength, cause a transition to happen, and measure resulting fluorescence, and that will give you basically give you a means to, say, get concentration, how much of that stuff is there is basically going to correlate with how much fluorescent signal you see. But then if you really want to make things interesting, you can sometimes even use that signal if you know enough about your molecule to get pressure, to get temperature, and all kinds of exciting stuff. You can use that fluorescent signal and see how it changes over time to get velocity. You can similarly use techniques where we seed particles into a flow in kind of a mostly non-intrusive way, track how those particles move or how groups of particles move to get velocity. So there are all and there's a long list of techniques like that we can employ, and we tend to work on improving those techniques, develop them with more advanced camera technology and lasers that are coming out every day. Really, the commercial market has really exploded in the high-speed sensor and high-speed laser area. So we're able to take advantage of some new technology out there to have some new applications of these techniques. And honestly, a lot of these techniques have been developed by the combustion community. There are many applications in flames because obviously intrusive measurements and things that are exploding or burning are kind of hard to do. So there's a lot of emphasis there. And they've been over time adopted by the fluid mechanics community as well. And then you want to look at a hypersonic flow. Those types of techniques, there just aren't a lot of applications when you go to Mach 7 that people have actually had a chance to try out, because there are some challenges. The pressures are very low, the flow is moving very fast, the time scales are short. So you're always hurting for signal, trying to find ways to boost that signal. And like I said, we're trying to measure fast. So now we have to measure things at hundreds of kilohertz, megahertz rate to really get the data that we want to get things time resolved. So those are some of the challenges that we deal with.
Mm-hmm. What about things like the Schlieren method? I know it only from university that there are also things like Schlieren method. Is this something you also use, especially for hypersonic flows?
Yes, for sure. And Schlieren is a really useful technique for us. It's actually generally one of the first things that we throw at a new measurement, because it is on its face qualitative in nature. So there are some ways that you can extract quantitative data, but at first order, it's a qualitative technique, but it does provide a lot of value in flow visualization. It's always great to try Schlieren the first time that you're running a model, so you can just see what's happening and understand what's going on. Is there anything funky that shouldn't be here? Are there any wave structures that we didn't expect? Is the flow separating in a weird place where it shouldn't? Or is this model performing perfectly just like it should, and we're ready to go on to other things? So Schlieren is really nice for that. It's nice to kind of and give you a big picture of what's going on. And so kind of give some background for people that maybe aren't quite familiar. What we're doing when we apply Schlieren is we're taking advantage of the fact that light rays can be bent, refracted by changes in density, changes in temperature. And this is the reason that you see a mirage on a hot day over a road. It's the reason if you ever look across the top of a candle, you can maybe see the background flickering a little bit. Mm-hmm. And so we're kind of using this to our advantage in the lab in somewhat scientific setup, but really the type of thing that a trained graduate student can set up in 30 or 40 minutes. And once you have the right optics, you can take advantage of the refraction of light and make measurements using a shadowgraph, which is kind of one level of simplicity down that's not quite as sensitive, or Schlieren. And so we use the Schlieren technique quite a bit. We can see shock waves, we can see expansion fans, we can see turbulent structures, and it is so sensitive that the rule of thumb that I give to my students when they're setting this up is if you rub your hands together to kind of get them hot and hold your hand in that Schlieren setup, you should be able to see thermals coming off your hand. Mm-hmm. And if you can do that, you know that you got it set up enough. You should be able to tell when the air conditioning kicks on in the lab, because you should probably see it. So it's a pretty neat technique with a lot of value. Like I said, it's qualitative in nature, but something that we've done, for example, is we have tracked shock structures over time and use that to actually extract a good bit of quantitative data. So if you get creative, there's some things that you can do.
Mm-hmm. I think to everybody listening, I think it's also possible to build something like a Schlieren method at home. So it's not that hard to build it actually yourself. So that's really, really interesting. You talked about expansion fans and shock waves. So during my research, what people commonly see is like videos from fighter jets. They've passed by, for example, at a beach or aircraft carrier, and you can see what is supposed to look like a shock wave, and then it's vanishing. This cone is vanishing and appearing again. Could you maybe explain how that actually works and what kind of misconceptions there are when it comes to expansion fans versus a shock wave?
Yeah, so this is one of my favorite common conceptions among aircraft enthusiasts is to kind of dispel this idea, one, of the sound barrier, and two, to kind of explain this vapor cone phenomenon that we see in a lot of these videos. And so you'll see these images and these videos often circulating online where there's this kind of cloud-like cone structure around an aircraft, and it is very often captioned as, you know, here's this fighter jet breaking the sound barrier, for example. And I've got a lot of problems with those types of comments. For one, there's no such thing as a sound barrier. It is true that there's a significant increase in drag that happens, mostly related to wave drag, as you approach the speed of sound. There's a reason that it took us a long time to have aircraft that could fly faster than the speed of sound, because the physics really does change when you approach that speed and you go transonic. Transonic is not a fun place to be. You kind of want to punch through that and get on one side of it or another. So there are some challenges with going supersonic, but there is no barrier. We can certainly travel faster than the speed of sound, and you don't necessarily hit a wall when that happens. So that's a bit of a misnomer. But also, the structures that you see, these vapor cones, they're actually the result of an expansion fan. And so an expansion fan, some of us are familiar with shockwaves, all right? A shockwave is what nature does to accommodate for a pressure difference, because when something is traveling at or, you know, near or at or above the speed of sound, because really what that means when you're moving at the speed of sound is that you are arriving at a location, you're running into air molecules before they know that you're coming. That's really kind of the simplest way to put it, I think, conceptually. The air molecules don't have time to communicate to each other that, hey, there's an airplane coming, get out of the way. And so a shock wave is what nature does to accommodate that, because at the end of the day, the air molecules cannot go through the vehicle. They do have to get out of the way. And the shock wave is what's going to do that for them, because they don't actually have time to do it on their own, like for a slower moving aircraft. But we've probably heard more about shock waves and are familiar with sonic booms, which is the sound generated by that big pressure difference. All right. Expansion fan is kind of the opposite of a shock wave. An expansion fan happens once that flow has a chance to turn back and to expand, basically speed up. All right. And go back to sort of its original position. So if you can imagine an aircraft showing up, turning the flow one way, the air has to get out of the way. And then it's able to relax back and expand again back to its original position. That's called an expansion fan. And that is a more gradual, gentle process. We can model it as isentropic, generally speaking. So relatively no change in entropy, which is not the case with the shock wave, which is very sudden and rapid and violent. But in an expansion fan, because that air is expanding, you get a temperature drop and you get a pressure drop, which can lead to ignition in the right conditions if you have sufficient humidity. And so this is the reason that we see these vapor cones for transonic and supersonic aircraft is it's actually caused by an expansion fan or some other similar phenomenon like a vortex or a flow separation that is causing a pressure drop and a temperature drop. All right. And so we can see these for a supersonic aircraft. We can also see them often. A lot of the best photos are actually for transonic aircraft, because many people don't realize for an aircraft moving, say, at Mach 0.9, not quite the speed of sound, the flow can accelerate over the airfoil to supersonic speeds. And so then you still get these same structures over the airfoil or other parts of the vehicle. So you can have some of these photos and the vehicle isn't even traveling at supersonic speed, and sometimes it's kind of hard to tell without having actually been there, or maybe having a video where you could potentially hear sonic to kind of, that's sort of a tell. But they are really neat pictures, just often misunderstood. So I like to clear that up when I can.
Mm-hmm. Also, the sudden appearance and disappearing of this vapor cone also is probably due to the local changes in the atmosphere then, rather than
exactly right
accelerating or decelerating.
Exactly right. Yeah. So that is going to be more of a result of just very local changes in humidity. The same reason you see clouds certain places and not other places, because the aircraft is not slowing down and speeding up that rapidly where the flow structures suddenly just disappear.
Mm-hmm. Yeah, you mentioned a good point, which is like a temperature change and also a pressure change. So when we look across a shockwave, for example, you have this kind of a step function when it comes to pressure and also temperature changes. I would be interested to know, like, how big are the effects and when do we actually account for thermal changes in the shockwave and also on the airfoil structure or maybe the whole aircraft that we're looking at? When does it become like dangerous, quote unquote?
Well, you get a step in pressure, for really just about any kind of shockwave, especially, you get up to Mach 2 or so, it matters. One example I like to give is because an area that I study is this thing called shockwave boundary layer interactions, which is kind of touching on what you're getting at, where if you have a shockwave that, say, is on an airfoil or that's standing up in front of a control surface or a fin that's generating its own local shockwave, that shockwave will impact the vehicle structure somewhere. All right, it's going to hit a wall, and we call that a shockwave boundary layer interaction because the shockwave actually impinges on the boundary layer that develops along the surface of a vehicle. All right, this kind of slower moving air that's close to the vehicle. There's this concept of a boundary layer for those that aren't familiar, because the air molecules do actually stick. We call it a no-slip condition on the vehicle surface at a microscopic level. And so you do have a velocity gradient close to that wall, where the flow is actually moving relatively slow over the vehicle surface, very close compared to further away. We call that a boundary layer. And so you can have shapes that hit that boundary layer, which really, for all intents and purposes, for most of us, just means it's hitting the vehicle body. And that can be dangerous. It creates very large pressure loads, very large acoustic and structural loads. And the X-15 hypersonic demonstrator, when that was flying back in the 60s, they had this test to look at a ramjet. And they had a dummy ramjet that was going to be installed underneath the vehicle. And they were going to fire it up and just see how it flew. There came a point in the test where they were supposed to dump the dummy ramjet because it actually hung below the landing gear, and so they wouldn't have been able to land safely if the ramjet was still attached. And there was a button on the in the cockpit to release the dummy ramjet, and the test pilot pressed that button a few times, but it indicated he didn't really notice anything happening. And then as he's flying by the runway, got a positive indication like, no, the ramjet's not there, so you get to land. Comes in and lands, and they do an inspection and realize that the ventral fin that was holding the dummy ramjet had completely sheared off, which was later discovered due to a shockwave boundary layer interaction. Mm-hmm. When you're moving at hypersonic speed, those are acting basically like a blowtorch, and they can cut right through metal, and you really is a very dangerous pressure and temperature load that happens as a result of those shockwaves. So it's really, it's a very active area of research, because if you have a shockwave impinging at a location that you didn't expect, your vehicle can fail. So it's really a phenomenon that needs to be understood. And there's a lot of active research in that area. But kind of the short answer to your question is that at supersonic speeds, those shockwaves and the resulting pressure loads caused by those shockwaves are something we have to think about as designers.
Mm-hmm. When it comes to the design of the airfoil itself, is there like any design changes you have to make as an engineer when it comes to like how the airfoil is actually modeled? For example, if we take the commercial aircraft and put it into hypersonic conditions, what would happen? Would it definitely fail?
Yeah, it wouldn't be happy. So for one, at hypersonic conditions, traditional commercial airliner materials are not going to hold up, because you're dealing with very high temperatures, and so the materials themselves would fail. And even you look at the SR-71 that was flying just a little over Mach 3, that could not use traditional Aeromaterials. There's some special alloys and things that they did to handle that heat. Even the Concorde wasn't, designed quite using conventional materials, and that was just a Mach 2. So that's definitely a consideration. And then, you get up to Mach 5 plus, you're dealing very, very hot. And so like aluminum, steel are not going to do well. Then from an aerodynamics standpoint, even for supersonic aircraft, there's a couple of things that happen differently to manage the changes that happen when you start going at high speed. So a lot of times you'll go and look at an F-22 or an F-35 and see there's a lot more sharp edges on those vehicles than you would see on a commercial airliner where everything is smooth and round, and that is because of the supersonic flight. There's a radar cross-section element to it as well, but in supersonic flight, you've got this idea of kind of the canonical diamond airfoil. And you actually, if you do a lot of low-speed aero, you're used to kind of smooth and streamlined shapes and rounded leading edges that make things nice and keep the flow separated. At supersonic speed, it's actually better to have something sharp that is going to punch through and create oblique shock waves as opposed to a detached normal bow shock. And in a lot of cases, that's going to be better, at least kind of for a certain range of high speed. And so that's why you see a lot of these supersonic and hypersonic vehicles that are very pointy, so to speak, have sharp leading edges in a lot of different places. Now, when you get to very, very high hypersonic flight, like re-entry type speeds, then you kind of do want to use a blunt body to help distribute that heat, because what happens is if you have something sharp, the sharp leading edge, those loads and temperatures are so extreme that I like to say, if it starts out sharp, it's not going to stay that way for very long. That's going to get eroded away and turned into something round. And you can see that with a lot of test articles as well. And so you actually put kind of as much surface as you can into the flow to aero brake and slow down and distribute that load a good bit. But that's kind of at those Mach 20 plus re-entry type conditions. So there's a few different regimes to consider. But long story short, a commercial airliner would not do well at Mach 5 for a variety of reasons.
When it comes to Mach, like also the distinguishment between all these Mach numbers, is there like a specific physical, let's say, derivation behind it where we actually set the Mach limits, like Mach 5, Mach 1, and so on? And maybe you could explain, especially for those who don't know where this comes from.
Sure thing. So just for starters, when we talk about Mach number, that is going to be the ratio of the velocity that an object is traveling relative to the speed of sound. And the speed of sound is basically, it's dependent on what type of gas. So speed of sound in air and speed of sound in helium are not the same, all right? But it's also dependent on temperature, all right? And so it changes depending on what type of atmosphere you're flying at or how high up you are in the atmosphere. So there's a lot to it, but roughly speaking, the speed of sound in air at atmospheric conditions is about 350 meters per second. And so if anybody plays golf, that's kind of I think the easiest approximation to make is if you're on a par 4 on a golf course and you're standing at the flag and you can actually see someone teeing off from the tee box. From the time you see them impact the ball with their swing, it'll be 1 second before you hear the sound of their club hitting the ball. That's kind of the type of speed we're talking about. And that's Mach 1 because that means the sound is traveling at the speed of sound. All right, about 350 meters per second, just shy of 800 miles per hour. So what happens is if something starts moving faster, then information can propagate in your gas, because that's really what the speed of sound is. Sound is just an acoustic wave. It's just a low amplitude acoustic wave. But it's really not just sound, it's all kinds of information, pressure distribution, basically. So it's really the speed that the molecule can respond to local changes in pressure. All right. So once you start moving faster than that speed, then it was kind of like I was saying earlier when we were talking about shock waves. The molecules don't know that you're coming until you're there. All right. So there really is at Mach 1 a relatively abrupt change in the flow physics and how we handle things. And there's different types of equations, different considerations in vehicle design. And it happens pretty rapidly, from Mach 0.9 to Mach 1.1. There's a lot that happens. Now, and so anything in that kind of 0.9 to 1.1 range, we usually term that as transonic. All right. So kind of in that transition period between subsonic and supersonic. And then above that point, we term things supersonic. And that's a fixed definition for the most part. But when we talk about something moving at hypersonic speeds, that's much more loose. Mach 5 that's a nice clean number. It's generally considered to be sort of the threshold for hypersonic flight. But as the John Anderson hypersonic text puts it, there's no flash of green light when you go from Mach 4.9 to Mach 5.1. Nothing, appreciably significant happens over a small range, but there is this kind of gradual change in conditions that happens. And once you get past Mach 5, what we're really looking at is you have immense heating that starts to take place, all right, to the point where your vehicle design is really dominated by dealing with those heat loads and high pressures. You can start to see chemistry changes in the air because the air that's processed across that shockwave can actually be ripped apart. The molecules dissociate. You can have a plasma start to form as well at even higher Mach numbers. So you have these chemistry effects that start to matter. And you also, if you look at some relationships for, some of the different coefficients and some of the things that we consider in design and in analysis, there are actually some equations that you can simplify for higher Mach numbers, basically setting the limit of M goes to P. There's some kind of curves that go flat, some relationships that you can simplify as linear. And so there's some things like that too. There's this kind of different hypersonic flow regime where you can make some assumptions. And then something I like to remind people is you get really, really high up there in Mach number, kind of the reentry type speeds. There's a reason that NASA talks when they look at reentry in terms of velocity. And we kind of stop using Mach number at a certain point because speed of sound gets sort of funky in terms of how you define it, because defining a temperature in those conditions is a bit weird. And, where are you in the upper atmosphere and what's the speed of sound in a rarefied flow? So a lot of times it's easier to talk about just velocity. And it's just, you're looking at kilometers or miles per second. It's fast. And whether it's Mach 25 or Mach 30 or Mach 35, it's fast. So anyway, there's kind of a slow gradient of what's hypersonic or what's not, but depending on what atmosphere you're in and what type of considerations you have, Mach 4 might seem like a hypersonic flow in some cases, and in some cases Mach 6 doesn't. So it's a bit of a loose definition, but we've kind of accepted as a community Mach 5 for simplicity's sake.
Yeah, that's super interesting, Chris. So maybe talk about is there a theoretical upper limit when it comes to the Mach number?
That's a good question. I mean, I think theoretically speaking, no. And like I said, there are a lot of these equations that, and you can linearize them. There's some kind of hypersonic airfoil theory and things like that, where we basically take the limit as M goes to infinity. So, there's no reason you can't go higher in Mach number. But if you want to look at some of the fastest things that have, are maybe relevant, things coming back from low Earth orbit and the space shuttle are in that Mach 20 to Mach 25 range. Moon, Apollo type reentry, Mach 30 to 35. If you want to look at something coming back from Mars or Jupiter, going to be even higher than that. So for all intents and purposes, that's kind of like the top end what we're dealing with. But there's no reason a meteor couldn't come through at Mach 60 or something. But kind of like I said, the relevance or the importance, basically, when you're doing a lot of analysis, the difference between Mach 30 and Mach 35, it doesn't really have a lot of basically a lot of meaning when you're crunching numbers, so to speak. But then you also have these issues of, like, you start going that fast and a lot of the assumptions you make deriving equations in the first place kind of fall apart. So it's a different flow regime. You're dealing with chemistry and non-equilibrium. So it gets to be a bit of a mess. But yeah, sort of like I was saying, you get to a point where it's really fast. and also most things, if they hit the atmosphere at Mach 40, they aren't moving that fast for very long, right? Because they're immediately starting to aerobrake and they slow back down into a lower speed regime.
Yeah. What would also be very interesting for me is, like, you mentioned the chemistry. Like, is there any numerical approaches or like special software that you could use to actually simulate that? Because I think it gets quite tricky, right? Because you don't have this classical, I don't know, ANSYS Fluent, what you're using then for your aerothermodynamical applications, but you probably have like a specific code which solves your equations in that sense.
Yeah. So there's a few different things. I mean, for the basic stuff, there's a really great, I think Virginia Tech made it, high-speed aero calculator, where you can get, shock relations and pressure differences across shocks and temperature differences across shocks. You can punch in any number you want. And that's sort of the kind of fundamental stuff that we teach in just an intro to compressible flow type course at the undergraduate or graduate level. And that does a lot for us. Those go a long way. And thankfully in our Mach 7 facility here at UTSA, we actually, even though we heat up to 700K, we're not seeing non-equilibrium in our flow. You need to be over 1,000K before you really start to have to worry about that. And so we haven't seen that, but to kind of answer your question, the non-equilibrium and the chemistry is very, very complex. And there's some, real gas effects equations that you can use. And there are some calculators online, I think, that you can use for that too, that will give you a better approximation of the, basically conditions across a shockwave. But for like the high Mach numbers, but also, trying to nail down the detailed chemistry for a more complex flow is really hard to do. There are people working on it. I think it's probably easiest to say it's an active area of research, and getting those models down and getting the predictions right in a reliable way. That's tough, but there's some really smart people working on it. One anecdote I like to give, the first space shuttle, STS-1, that almost was not able to land as intended. We almost lost that vehicle because we did not quite properly account for real gas effects and changes in the air chemistry downstream of those shock waves. And there actually wasn't enough travel in some of the control surfaces, and they pretty much had to max out at the design condition, which was supposed to have a good factor of safety in it, but they just weren't responding as designed because of the changes in the chemistry and those real gas effects happening, which are really challenging to account for the right way. But it's difficult to recreate that on the ground, and so you kind of start running into challenges where you need better models, but it's also hard to even get the experimental data to arrive at those models.
I think maybe going one step back, when you mentioned the Apollo 13 mission, I think there's a video of a re-entry of that capsule, and I was thinking, like, when it comes to the material, I think you call it ablation. So basically the material that you account for on the surface is basically designed for actually for ablation. Is there like kind of research going on in terms of like composite materials where you can actually reuse the shuttle multiple times? I mean, when we talk about SpaceX, everyone knows them. What kind of research is going on in that area when it comes to materials?
Yeah, I mean, that's a huge area. We've got legacy ablators, and really for the audience, that basically means material is designed to burn away during the reentry. It's kind of a sacrificial layer that helps keep everything else cool. You've got different types of ablators, different types of thermal protection systems, some reusable, some designed to burn away and be used once. But predicting how much of your ablator burns away and how that interacts with the rest of the flow, that's not something we're good at right now. The Mars Science Lab mission, it only used about 8% of its heat shield. So there's a lot of extra weight that got packed on that thing. And I think the Curiosity lander, it was a similar deal. And so, that's a tricky problem to solve. Materials research and development is very, very active right now. I'm trying to develop reusable materials, composites, woven carbon composite that's got, a resin mixed in with it. That's a really big area of research. And, if there was some really great lightweight reusable TPS that we could model well, that's kind of the holy grail. That would make a big difference in vehicle design. But we're not quite there yet. So it'll be interesting to track, kind of how that happens. There's been a lot of advances in material development, but this is, again, another area where reproducing in all the conditions of hypersonic flight on the ground, you just can't really do. And so you're flying blind a little bit in these material designs, and a lot of times you don't know exactly how well they're going to perform until you fly them. So it's a very tough area to work in. But there's definitely a need there for continued development of these advanced materials.
Very interesting. Maybe one of the last questions, Chris, would be what's something that's most fascinating, maybe puzzling to you in terms of hypersonic aerodynamics? I mean, you mentioned the Shockwave boundary layer interaction, right? This is something where you're actively researching on, but maybe there's something else which really is fascinating you on a day-to-day basis.
Yeah, I mean, I do a lot of stuff with the Shockwave boundary layer interaction. I think maybe another area that I'm really interested in is just on the propulsion side. How do we make these vehicles? How do we get these things to fly? Right? Because we have these boost glide vehicles that get shot up into space, and then they basically come down like gliders, and they can really just be rocket propelled and then they glide. But if you want something that is going to travel for an extended period of time in the atmosphere, then you need an engine that's going to fly, and it's probably got to be air breathing because you can only carry a certain size rocket. If you want a long duration flight in the atmosphere, it needs to be air breathing. And so, we're looking at rotating detonation engines. We're looking at Ramjets, Scramjets, some combined cycle stuff, looking at more advanced turbines that can process air at higher speeds because our turbines are really limited to kind of Mach 2.5 or so right now. And so kind of developing that next generation of propulsion tech is an area that's really interesting to me because you've got shockwaves that are coming into play in your engine. You have a lot of heating and pressure loads that those engines have to deal with. And then you have this kind of lighting a match in a hurricane problem where you've got this very high speed flow, but how do you keep the flame lit? How do you get the fuel to mix properly? How do you get it burning efficiently? There's a lot of really neat problems on the propulsion side as well.
Maybe just before we jump to the closing the podcast with a bit of resources from your side, just quick and briefly the definition, or maybe like the advantages and disadvantages between scramjets and ramjets. I think that would be interesting.
Yeah, so really the difference between ramjet and scramjet is going to be dictated by how fast you're moving, right? And so a ramjet, and the SR-71 had a combined cycle ramjet turbine that by the time it was flying at Mach 3.2, it was going about 80% off of the thrust from the ramjet. The turbine wasn't doing nearly as much at that point. Really what that means is you've got a straight duct and you are shocking down the air to subsonic speed, but that shock wave is actually giving you your pressure ratio instead of some like rotating machinery or a turbine or something like that. So you can use geometry to create a shock wave and get your compression that way, basically with an open geometry. That's in essence what a ramjet is. And when we talk about ramjets, it means that supersonic air coming in is shot down to subsonic speed inside the cavity. A scramjet, on the other hand, you're moving so fast, often hypersonic speed, that even though you shock the air down, it's still moving at supersonic speed inside your isolator and inside your cavity, which kind of presents this new set of problems. And so really, in essence, if you want to look at advantages versus disadvantages, advantages of a scramjet is you can go faster with a scramjet. All right. Scramjets are designed to operate at higher Mach number range. Ramjets a little bit simpler, a little bit easier to pull off because you've got subsonic air inside instead of supersonic. But a lot of times what you'll see now are, scramjets and ramjets being designed as like a dual mode is what they're called, where they can go back and forth between ramjet and scramjet mode depending on, where you are in your flight regime. But for both of those engine types, a big downside is they cannot start from on the runway. For example, you're not starting at zero thrust. You need to get up to supersonic speed before those can work because you need shock waves. You need high speed air inflow. So they will have to be part of some sort of combined cycle engine, whether it's a combined cycle turbine or if you have like a rocket boost up to a certain speed, and then you can operate those.
Very well explained. I think we can pull that out from the podcast and put it as a separate clip on YouTube for people interested in what the difference is between a scramjet and a ramjet.
Great.
As a closing remark, Chris, thank you so much for being on the podcast today. Any closing remarks when it comes to textbooks? Because I know a lot of people will ask about textbooks on hypersonic or aerothermodynamics, and also resources that you would generally recommend to the audience.
Yeah, so the first thing I recommend is the John Anderson Modern Compressible Flow textbook. Also the Anderson Hypersonic book. Those are both very well written, easy to follow, easy to read. I think those are great resources. And even if you don't have the background in fluid mechanics, like the Munson Young Okishi Fluid Mechanics book is great. So there's a lot of good places to go there. And honestly, NASA has some really good resources online as well that you can look up. And then there's a Virginia Tech Aerodynamics calculator that y'all can have fun with. That's pretty easy to use. It saves you the trouble of having to look things up in tables in the Anderson book, for example. Also, I'd encourage people to follow me on Twitter at Dr. Chris Combs, and you can keep up with what I'm doing in research. And I post some educational threads from time to time also.
Yeah, that's what I wanted to say next, Chris. So follow Chris on Twitter. He posts amazing stuff, or retweets also amazing stuff. So make sure to follow him. And I will put every link from the books you mentioned down in the description. With that being said, we learned a lot today. I learned a lot today about hypersonic aircraft. Maybe one last thing, Chris, I wanted to talk about is where do you see maybe the future going of hypersonic flight, especially when we talk about commercial aircrafts? Because the idea of it is maybe super fascinating, but maybe your last 2 cents on where the future is heading towards.
Yeah, it's going to start small, I think. We've seen, for example, Hermes get a contract to look at maybe an Air Force One type transport, or a transport that could take maybe a small group of people. I think that's kind of the first type of stuff that you'll see. Maybe in the next 10 years, we have a prototype for something like that, but there's a lot of problems still to work out. So it might still be a while. I think that the SpaceX Starship type suborbital or orbital type stuff is going to outpace that for the time being, and you'll see that as kind of a point-to-point around the world transport first. Maybe in our lifetimes we see a commercial Concorde type aircraft that can go at hypersonic speeds, but we've probably got to solve the scramjet problem first, and we've still got a little ways to go to work on that. So keep an eye on some of the defense programs that are out there. Hawk HWC is a DARPA-led project that just had a test recently. The Aero ARW Lockheed Martin vehicle has been kind of awaiting a test. So we might see some air-breathing engines tested in the next year or so. That's kind of the first step. And if that technology gets more mature, then maybe you see them integrated into a larger airframe down the road. Great, fascinating. Very, very excited to see that in the future. Chris, again, thank you so much for being on the show. Learned a lot, and I think the audience does as well once the podcast comes out. And I think we see each other on Twitter then. Okay, all right, sounds great. Great talking to you, Jousef. Thank you. Thank you. Bye-bye.